We haven't tuned this at all yet, so the image looks terrible right now. So the next step is to do the tuning of the feedback circuit. The first thing that we want to do is to set the amplitude set point, which is over here. So if I click on that, it turns blue. Remember, this is what target oscillation amplitude is the feedback circuit trying to achieve. So the bigger that is, the more lightly I'm tapping on the surface. The lower it is, in order to lower that amplitude, I'd have to hit the surface harder. So I want to tap on the surface as little as possible so as to damage the sample as little as possible. In order to adjust that, I look at this bar graph down here, which shows the position of the Z piezo that's controlling the base position of the cantilever. So there's an oscillation piezo, that's a separate thing, and then there's a Z piezo that kind of moves slowly up and down. And right now, you can see that the little mark is roughly halfway between fully extended and fully retracted. So if I start increasing the amplitude set point by pushing the right arrow button, each time I push this arrow button it increases this by a few percent, you can see that that line is moved just a little bit. I push it again and it moves further off. Now I'm basically completely off the sample. It's like this. It's oscillating but not touching the sample, and so the image looks like crap because it's not really imaging. Now I want to come back on until I'm just barely touching the sample, so I press the left button, this goes to the left, press it again, it goes to the left a little bit more, press it again, it goes to the left a little bit more, press it again. That time it hardly changed at all. So what's happening is in those first few presses I'm kind of getting down into the water meniscus that coats the sample, and that's giving a little bit of damping, but it's not like hitting a hard surface. As soon as I start to hit the hard surface, then even a small extra decrease in, a small extra downward movement in Z decreases the amplitude a lot. So when I click to the left on this arrow now, you basically won't see this changing at all. It is changing very slightly, but hardly any. So the recipe again is first we get it so that it's basically off the sample, that is, it's moved quite a bit to the right. Then I click on the left arrow and I'll wait to see the response until the first time where I essentially don't see it move at all, which was right there. It didn't move at all. Now I click 3 more times to the left. 1, 2, 3. Now it's on the sample, and you can see the image that's accumulating here sort of is a sensible image for this rough, grainy surface. The next step is to adjust the integral and proportional gains of the feedback loop. The feedback loop is, again, its function is to try to maintain a constant amplitude of vibration as I move over the sample surface. And so when it gets to something that's high on the sample surface, the feedback is going to use the Z piezo to retract a little bit so that the amplitude of vibration doesn't go down too much. However, if it's set to a feedback condition that I'll refer to as being too tight, that is, these gains too high, then when it first starts to detect the amplitude going down a little bit, because I'm starting to hit something on the surface, it's going to retract too much, and then the amplitude will suddenly be too big, and it'll say, oh my gosh, and it's going to approach too much, and then it's going to say, oh, it's too small, and it's going to retract too much, so it goes into this oscillation mode. That's obviously not very good, but if I don't have it set tight enough, then it's going to take too long to respond to changes, and it's not going to track the sample surface very well. So basically the recipe is start by adjusting the integral gain until I actually see the oscillations, and then I'm going to back off until the oscillations go away. It's helpful to have a part of the sample that's relatively smooth to do this adjustment on. This is a sample that has a lot of fine-grained structure, and so to get a part that's effectively pretty smooth, I'm going to change the scan size to a half a micron. So I'm going to type in 0.5, hit the return. Now it's changed to 500 nanometers, which is half a micron. Now the features on the surface of the sample look relatively big, and that will allow me to see the effects of the oscillations more clearly. There are 2 images that are being displayed, and what is being displayed here is controlled by these 2 boxes, channel 1 and channel 2. By default, channel 1 is set to height, that is, it's showing you the topography of the sample, and channel 2 is set to amplitude, that is the vibration amplitude. If the feedback system were working perfectly, the vibration amplitude would be perfectly constant, and so this right image, which is showing us the amplitude, would not show anything at all. But you can see it's kind of a little bit noisy right now, but because I'm talking mostly, you can see that it does show something, and that's because when the cantilever first encounters something on the surface, it takes a short time for the feedback system to react, and during that time the oscillation amplitude would be reduced, and then when it drops back off the other side, it takes a short time for the feedback system to react, and during that time the oscillation amplitude will be a little bit higher than the target. So what I'm going to do again is highlight this integral gain, and I'm going to increase it until I start to see the oscillations on this screen, and I have to stop talking so that you'll be able to see them more clearly. I'm also going to speed up the scan rate. Right now since I'm only imaging at half a micron, I could speed this up to 2 Hertz. And up here are the suggested scan rates from Marko Radosavljevic for various different scan sizes. So basically 3 microns and below, 2 Hertz is okay, and we're well below that. And that will just allow us to do the tuning a little bit more quickly. You can see when I stop talking that we get a relatively clear image here without much structure on it. Now I'm going to start increasing that integral gain by highlighting it and then pushing the right arrow 1 click at a time until I start to see hash appear on the screen, and that indicates that the system is oscillating. I'll be quiet for a minute so we can see what it looks like when it's not oscillating, and then you'll probably hear the clicks on the camera. There, you see those bands of quickly, I don't know if you can pick this up on the camera, but there are bands of quickly alternating white and dark, and those are basically where the amplitude is suddenly going from really high to really low, and that's because the feedback is going from all the way up to way down and all the way up and back again. So that's the system oscillating. So now I'm going to push the left arrow until those go away. In that case it only took 1 click. Very often it might take more than 1 click to make them go away. They're still there, so I'm going to push it again. Now they're basically completely gone, but I really don't want the system to oscillate while I'm trying to take a serious image, so I'm going to push it 3 more times to the left to make sure I'm well away from oscillation. That's how I set the integral gain. The proportional gain is always set to be approximately 3 to 4 times this, and it doesn't matter exactly, so it's already set to about that. So we're basically all tuned, and we're ready to take images.